audio and video content. I think video now. The audio. So then we will start. Please confirm with the audio and video clear or not. Audio and video clear or not. Please confirm. No. Okay. Thank you very much. So again we'll we'll discuss about the conservation of energy applied to an open system, and that system is number second. Then we will discuss about application of the entropy. That means we have to develop to understand the formula which is applied in the entropy chapter, and what is the consequence of that entropy. Okay, what is the consequence of the entropy? So my dear, we already studied that steady device is your throttling process. It is your throttling process. Start करो आप start. Okay, so sorry for that one. Please confirm the audio and video clear or not. Please confirm that audio and video clear. Everyone, please confirm audio and video clear. Please confirm audio and video clear or not. Please confirm. Everyone, please confirm audio and video clear or not. If it is clear, then we will start the session of formula revision. Please confirm audio and video clear or not. Please confirm, beta. Okay. Now it's okay. I think now it's okay. Okay. Now it's okay. Okay, no problem. So what is the okay? Thank you everyone. So what is the thank you everyone. Now so today we will discuss the two part. That means a first part is the first law applied for the open system, and that open system is your unsteady device. Okay, that means the property will be dependent on the time. That means the property of the system will be depends upon the time. That means the changes with time. Number first. Number second, then we will discuss about the entropy and what is the consequence of that entropy. Okay, we will also discuss. Now, now my dear, so we'll already see that the consequence of the first law for the open system and the system is steady. That is the first example is your the first application. It is not example, it is a first application, and that application it is your throttling device. So we already know that in the throttling device the process is that means the inlet of the throttling and exit of the throttling, the enthalpy is same. And we also discuss study that the throttling is not necessary that it is a isenthalpy process. So if you throttle the ideal gas, why? Because we know that for the ideal gas with a less accuracy, we treated as an ideal gas as a perfect gas, and perfect gas Cp and Cv are the independent of temperature. So we can write enthalpy as a Cp T1 and equal to Cp T2. So Cp cancels, T1 equal to T2. That doesn't mean that if you throttle the ideal gas, the temperature is constant. No, yes, temperature at inlet and temperature is exit is constant. Okay, sir, explain why throttling is not isothermal process. Isothermal process. Yes, we will discuss already. Okay, but I am very happy to explain again. Okay, no problem. I will discuss that one. See, so. See, as we know that this is your throttling process, that means this is your cross section I1 and this is your cross section 2. This is your cross section 2, and we know that that enthalpy at a cross section first is approximately enthalpy at a cross section 2. Now, for the ideal gas, we know that H is equal to Cpt. For the ideal gas, we know that. Now, if you write Cp T1 is equal to Cp T2, and for the same gas Cp is constant, so this Cp and this Cp will cancel out. So this Cp and Cp cancel out, so it may be T1 is approximately equal to T2. Yeah, you can say that T1 equal to T2. That means what is the temperature before throttling is the same as the temperature after throttling. So, but if you draw the diagram, let's suppose this is 1 and this is 2. Let's suppose we have to draw the diagram of temperature versus length. So let's suppose this is your temperature T and this is throttling length. Let's suppose this is your length, yeah, X. Now, initially at inlet, the inlet temperature, let's suppose T1, and this is your exit. Let's suppose this at X is equal to L, there is a exit. So let's suppose there is a temperature T2. Now, my dear, you know this, yes, this temperature T1 is equal to this temperature T2. Yes, it is there, no problem. That means this temperature T1 is equal to this temperature T2. But what is the path you don't know? That means why you don't know the path? Why? Because you don't know in between the locus, between the inlet and exit condition, you don't know the locus. Why? Because we already know that throttling is a highly irreversible process. So we cannot draw the path in between. So it may be temperature will reduce, it may be temperature will increase, and it may be temperature will constant. We cannot say. That means if this path is follow, so temperature will increase. If this path follow, temperature is constant. If this path follow, temperature is decreasing. So we cannot. So throttling of an ideal gas is approximately isothermal. That is false. Now I hope that is clear. This is clear. Okay. So throttling is a not isothermal process. Iso matlab that means the temperature throughout same from inlet to exit at each and every point. Okay, so we cannot say like that. Okay, thank you very much. Now then we have to already discuss about that is the throttling, and we also discuss about that what is the application. If you apply the refrigerant condition, that means it's throttling condition. We already know that means if there is a refrigerant, let's suppose there is a refrigerant, that means this is what, let's suppose this is what T and this is your S diagram. Let's suppose this is temperature and entropy diagram, yeah, pH diagram. anything. Okay, so let's suppose this is your P, this is your P, and let's suppose this is your P, P and H diagram. Let's suppose this is P and H diagram. No, P or not H. Okay, you can write like that. Okay, no. Let's suppose this is T and S diagram. Okay, TS diagram. So if you draw the diagram, there is a saturation curve. Let's suppose this is a saturation curve. Okay, this is a saturation curve, yes, saturation dome, and this point is a critical point. Now, if you draw the pressure, that means during the throttling, the pressure will reduce. That is the fix. During the throttling, the pressure will reduce. That is the fix. That means inlet to the throttle have a high pressure P1, and exit from the throttle, it is a low pressure P2. Okay. In the refrigeration, the start of the throttling from the saturated liquid line. Start of the throttling in a saturated liquid line. Now it will throttle. So during the throttling, we know that it is a highly irreversible process. So entropy will increase. That means it will increase its entropy. So let's suppose this is 2. So 2, it is your liquid vapor condition. That means 1 is your vapor liquid, and 2 it is your liquid plus 2 it is your 2 point, it is your wet region. That means here liquid plus vapor both are there. That means during the throttling, as we know that enthalpy is fixed, H1 is equal to H2. Okay, so this is your throttling process. Now, why the temperature will drop during this capillary device? This is a capillary. In the refrigeration, why the temperature will reduce? Please tell me. Let's suppose there is a container. Let's suppose there is a container. In this one, at point 1, there is a saturated liquid. There is a saturated liquid. So this is your saturated liquid. Okay, saturated liquid. Now you have to reduce the pressure. If you reduce the pressure, why? Because during the throttling, pressure will reduce. So if you reduce the pressure, the liquid start evaporation. Liquid start to be evaporation. That means at a point 2, there is a partially there is a liquid, and there is evaporation will start itself. So and partial there is a vapor. So this is liquid, and there is a vapor in a container. Let's suppose there is liquid. Now, my dear, if something is vaporized, and this vaporization will be done due to the low pressure. Why? Because during the throttling, the pressure of the fluid at the exit condition will reduce. So the pressure will reduce. So automatically the reduction of the pressure is such that it will cross the vapor pressure of that corresponding fluid. So it start its boiling or evaporation. So once it start the evaporation, for the evaporation energy will required. For the evaporation energy will required. So who is the responsible fellow to supply this energy? Who is the responsible? That means from where this vapor, this fluid, that means vapor fluid, want to vaporize to take the energy from where? Liquid itself. So from the liquid, the energy vapor will take energy to the vaporization. Why? Because vapor have a high energy level and liquid have a low energy level. So it will take the energy by the vapor to the liquid. By the vapor to the liquid, it will take the energy. So automatically the liquid refrigerant will reduce the temperature. Automatically the liquid refrigerant reduce the temperature. Clear? Liquid. So that's why while the capillary, that means in the capillary tube, when the refrigerant is passed, the exit condition have a very low temperature. Very low temperature. So if you solve this problem according to this data, so that is the consequence. What is that? The temperature of the refrigerant drop by, see, temperature of the refrigerant will drop by 53 degrees centigrade, like approximately. during this throttling process, temperature will drop. Why the temperature drop? We'll already understand. Throttling. Also note that 34% of the refrigerant will vaporize. Yes. Why? Because at a point 2 there is a liquid plus vapor. So 30% of the liquid, 30%, that means from the liquid 30%, 34%, approximately 34%, that means 34.34 is your vapor. It is your vapor. That means if you calculate the dryness fraction, if you calculate, that is your 34%. If you calculate dryness fraction, so 34% of the refrigerant vaporized during this throttling process. 30%. Okay. Now, and the energy needed to vaporize, this refrigerant is absorbed from the refrigerant itself. Absorbed from the refrigerant. Yes, throttling is an irreversible process. Correct? Yes, correct. Throttling is an irreversible process. Then, yes, throttling is an irreversible, highly irreversible. Why? Because very fast process. Very fast, rapid process. Okay. So, it will take, that means temperature will reduce. Why the temperature will reduce? Why? Because it will convert into the vapor of that liquid refrigerant. The vapor required the energy, that energy will take by the vapor to the liquid refrigerant, so that the liquid refrigerant have reduced its temperature. That's why we use the capillary tube act as a throttling device in the refrigerating system. Clear? In the refrigerating system. Yes, throttling is an irreversible process. That's why delta S will be greater than 0. See, throttling is a irreversible process. Correct. Now, so this is the precisely the application of that, and this is a very important application consequence in the thermodynamics. Now, we will start. Oh, is there any problem for up to this one? Please ask to me, no problem. Now, we will start the steady flow process for the open system, unsteady flow process. So, unsteady or steady, see, this is like a throttling. My dear, I give you one very good information. See, this is a throttling wall. For supply, there is a constraint passage. So, again, this is a throttling wall. So, this is throttling wall. So, if someone asks you, please listen carefully. Someone asks you, I will take, this is our inlet section. Someone says that, no, I am taking, this is our inlet section. Is there any difference? Please tell me. Is there any difference? Please tell me. If you take inlet at this section, or if you take inlet of this section, is there any problem? I will take inlet to this control volume is at this point, or either we will take inlet of this control volume at this point. Is there any mistake? Is there any conceptually mistake? Please tell me, is there any conceptual mistake? Yes or not? If we take, this is our inlet of this control volume, or either we take inlet of this control volume, is there any conceptual mistake? Please tell me. This is the very subtle concept I am telling you. The answer is no. Why? 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 Because this is your throttling process, and throttling, either you take enthalpy at this section is the same at this section. That means either you take enthalpy. Why? Because if you take a throttling, so throttling, it is an inlet, it is an exit. It is an inlet, it is an exit. It is an inlet, it is an exit. So either you take either you take a control volume. If you take a control volume, this one, so the inlet of this one, either you take at this position, or either you take this position. There is no any conceptual mistake. Why? Because let's suppose this is throttling, and throttling, it is a I and it is a E. So HI is approximately HE, and if you take, this is our control volume, so this is our inlet according to this one. So either you take inlet of this one, or either you take inlet of this one for this control volume. There is no any conceptual mistake. This is the interview question. Okay, so don't bother about ki sometime the teachers will take this control volume, and sometime the teacher will take this control volume. So you don't bother about ki sir, why you are taking this one. No problem. You take a control volume. That means you take a system either this or either this. There is no any problem. Clear? Clear. So that is the very important information I want to share you. So what is the consequence of this one, beta? So we will start for this one. Okay. 1 second. Now that means, see, what is this is your charging. This is the problem of charging. This is the charging. So what is the difference between the first law of thermodynamics for open system for steady and first law of thermodynamics, that means conservation of energy for unsteady? What is the difference? Why? Because we have not neglect the rate basis of the change of control volume. We are not taking. That means if you write the equation, so there must be a internal energy, that means there must be a property of the system we have to take on the rate basis with respect to time. Why? Because that is your unsteady flow problem. That is your unsteady flow problem. That is your unsteady flow problem. So mind it, beta, what is the equation of this? See, many processes involve changes within the control volume. Many process changes within the control volume. Changes within the control volume, my dear. Changes within the control volume. Such process called unsteady flow or transient flow. This term always remember. Transient. This term student get confused. What is the transient? Transient is nothing, which is that means in this flow the property of the system will change, and system, it is a control volume type. Some familiar unsteady flow process are charging of rigid vessel from the supply line. This is example. Second one, discharging of fluid from the pressurized vessels. Yeah, you can discharge. Driving a gas turbine with the pressurized air storage. That means if you taking the gas of a large container. Inflating of the tire or balloon. Cooking. This is the very common example you always seen. Cooking with ordinary pressure cooker. That means if you have a pressure cooker and that cooking the food, that is also an example of unsteady or transient flow problem. Now, what is the energy? What is the equation of this one? What is the equation of this unsteady? So, my dear, that is the equation. What is that? We already know that. What is the equation of the steady flow? What is the equation of the steady flow? So, that is the equation of steady flow. I will write here. That means conservation of energy, COM, conservation of energy, conservation of energy for steady flow device. So you know that is okay. That means already you have to write that. This is your energy, conservation of energy of an this is your equation. This is your equation of conservation of energy for the steady device. Okay. Now for the unsteady device, we have to write unsteady. Unsteady device. What is that? Please see. Q, heat transfer, MI, inlet. So in this conservation of energy, if you apply the conservation, there are four terms. There are four things. First is I1, second is 2, third is I, fourth is E. You have to always notation this one. This 1 and 2 for the system, and this I and E for the section. For the section. Why? Because there is, why you are taking 1 and 2 precisely? Why? Because here property will change. So property of the system will change from point 1 to point 2, and also property will change from inlet to exit. So here there are in this content unsteady, we have to notate at a 4 terms. So these two are for the system. For the system. And these two are at the section. At the at the section. Okay, these two are for the system and this is at the section. So what is that? MQ plus MI or I, that means the mass will transfer. So we already know that where the mass will enter or exit from the control volume, what is the energy associated? The energy associated is enthalpy plus kinetic energy and plus potential energy. So here it is your HI plus VI square by 2 plus GZI. So this is energy associated. So this is in is equal to change. Change is what? M2. M2 and this 2 it is your for the control volume, and for the control volume that means a system there is internal energy U2 plus V2 square by 2 plus GZ2 minus M1 U1 plus V1 square by 2 plus GZ1. Clear? Okay, so this is for the system plus exit, mass at exit section, enthalpy at exit, velocity at exit by 2 plus GZE plus work. That's it. That's it. And in the for the if you make this equation for the steady, you make the equation for the steady. So for the steady, this term is 0. This term is 0. That means there is no any change within the control volume. So this term is 0. Only this Q minus W. That means if you write like that, sorry, Q minus W, this is equal to this MI ME like that, MI HI plus VI square by 2 plus GZI minus this is your this Q minus W, so this is your minus, so put here minus. That means ME, first write ME HE plus VE square by 2 plus GZE, okay, minus of MI HI plus VI square by 2 plus GZI. This is at the section. So this is at the section. You have to take like plus this one. So this is at exit and inlet section. Plus this is your plus. So plus M2 U2 plus V2 square by 2 plus GZ2, okay, minus M1 U1 plus V1 square by 2 plus Z0. Now my dear, I give you one subtle concept for this one. In generally in the steady flow, charging discharging like thing is there. So in this case, if there is a charging discharging, so generally the change in kinetic and potential energy is 0 in general. That means you have to neglect this sum in general to remember this equation. In general, this term and this term, one second beta, this term, this one is 0. Okay, this is also change in kinetic and change in potential energy at inlet and exit is 0. So in generally the equation it will reduce in this form: Q minus W is equal to MEHE minus MIHI plus M2U2 minus M1U. Just you have to think like that. Now, my dear, there is a single inlet and single exit. That means a single stream device. That means Mi is equal to Me is equal to M. So you have to write like that. M He minus Hi plus M2U2 minus M1. That's it. That's it. That's it. This is your equation. This is your equation. Clear? This is your equation. Nothing else. Now, if you apply this equation into the one question, there is a one question I have. That is a very important question, this question. Please try it. Try this question. See, what is that? I will read this question, then I will solve it. This is the very good question. Why? Because this question gives a lots of insight. What is that? Please read that. A rigid insulated tank is initially evacuated, is connected through a valve to a supply line that carry helium at 200 kilopascal and 120 degrees centigrade. Now the valve is open and helium is allowed to flow into the tank until the pressure reaches 200 kilopascal, at which point the valve closes. Determine the flow work of the helium in the supply line and the final temperature of the helium. Okay. So what is that? We have to take something. Please think, Vita. What is that? See, a rigid. Here the term is rigid. That means rigid. That means a volume is constant. Clear? Volume is constant and there is no any electrical device. It is installed. There is no any electrical paddle wheel. Nothing is. So for this one, we have to write the work transfer is 0. No problem at all. Work transfer is 0. Now, second term, insulated. If the term is insulated, that means no heat transfer. So no work and no heat transfer is there. Now, tank is initially evacuated. Initially, what tank? The tank, it is your system. So you have to take, this is our system like that. If you take, this is our system. This is our system. Let's suppose this is our system. Let's suppose this is our system. Okay. This is our system. This is our system. So this is our system boundary. This is our system boundary. Okay. Now, the system is initially evacuated. So for the system, let's suppose there is a 1 and after it will charging, the system property goes to 2. So initially evacuated, that means M1 is 0. M1 is 0. Now next, connected through a valve to a supply line, connected to a supply line, okay, that carry a helium. That means this, in this one there is a helium and helium act as an ideal gas. So this is your ideal gas. Ideal gas, clear? And this helium, it is at 200 kilopascal and 120 degrees centigrade. So what is this one? That means the helium, that means the supply line, and the supply line, what is the pressure of the supply line temperature? That will be cross to this boundary. So this boundary is I, inlet. This boundary is inlet. So it is Pi and Ti it is given. Pi and Ti it is given. Okay. Now the valve is open. When the valve is open, the helium is allowed to flow into the tank. flow into the tank until the pressure reaches at 200 kilopascal. That means the tank reach the pressure at 200 kilopascal. That means this is a final. That means this is P2. At which point the valve is closed. That means when this tank is full of that pressure of 200 kilopascal, that means equalized pressure, valve is closed. At which point the valve determine the flow work. What is the flow work, beta? What is the flow work? P into a specific volume. This is your flow work. P into a specific volume of the helium in the supply line and also final temperature of the tank, that means T2. That means T2. Read the question very carefully while you have to solving the unsteady flow problem. And all the property R value it is given, Cp value and Cv value is given. Now start this problem. My dear, for the start of this problem, just take one precaution I am telling you. What is that? Please see this one. 1 second, beta. Okay. So there is your section I, section E, state point 1, state point 2. These are the 4 leveling. Write down. Now initially, what is the pressure? Pi 200 kilopascal. What is the temperature? Ti 120 degrees centigrade. Okay. And it says that the tank initially evacuated. That means M1 is equal to 0. M1 is equal to 0. Initially evacuated. Now, after opening the valve, tank a final pressure it is given. How much? P2. It is equalized 200 kilopascal. Clear? Now, M2 we don't have value. M2 we don't have. Exit, there is no any exit. So exit it is 0. Why? Because this is charging. These are only entry. These are only entry, no exit. So exit, this exit is 0. That's it. That's it. That's it. So first apply the conservation of mass. What is the conservation of mass? Mi minus Me is equal to M2 minus M1 of a control volume. This is your conservation of mass. So there is no any exit. Initially evacuated. So what is the balance? That means what is your M2 is the same as Mi. Is the same as Mi. So M2 is equal to Mi. I is where, beta? I is what? I is what? Inlet to the I is what, beta? Inlet to the control volume, and that is also called line, supply line. Supply line, inlet. See, what is the I? I is this one. And what is the property of I? Same as the property of the line. That means supply line. So always remember, I is nothing. I is the property of a supply line. That's it. I is what? I is a property of a supply line. That's it. That means I is your supply line. And what is 2? What is 2? What is 2? What is 2? 2 is the tank. 2 is the tank. So this is the property of tank. That means tank mass is the same as the mass which is supplied line. That is okay. That means you can write like that: mass of a tank is equal to mass of a line. Mass. This is your understanding. Please try to understand the language of a thermodynamics. Without understanding the language, you cannot solve the problem. Now, apply conservation of mass, conservation of energy. That's it. Apply the conservation of energy. Okay. So there is nothing tell about the change in. So we have to take the system is stationary. System is stationary. That means change in kinetic energy and change in potential energy is negligible. Okay. Now write that equation. That means there is also says that there is a adiabatic, that means no heat transfer, and there is no any working device, no work transfer. Why? Because this is rigid and there is no any electrical paddle will work. So if you write this equation, Q is 0, W is 0, and if you write this one, Q is 0, W is 0, ME is 0, here in this equation there is this is 0, this is 0, exit is 0, initially evacuated, this will 0. So what is that? M2U2 minus M2U2 inlet mass. Yeah, inlet mass is there. It is not like that. One second. Exit is there 0. Initially it is 0. That means M1 it is 0. So M2U2 minus MIHI is equal to 0. That means M2U2, if you apply M2U2 is equal to MIHI. This is okay after the apply of conservation of energy. Now M2 is equal to Mi. So this and this will cancel out. So what is that? U of tank is equal to H of line. Okay. And helium, it is an ideal gas. So we can write here U is what? For ideal gas. Ideal gas, what is that? H is equal to CPT and U is equal to CVT. Clear? So put here U is equal to CVT, a tank that means 2 is equal to CP line, that means TI. So if you resolve this one, what is that consequence? That means T of tank is equal to Cp by Cv, Cp by Cv of the line, T of line. Now my dear, Cp and Cv value it is given. Here Cp is higher than Cv. Please see this. Cp is 5.1926, Cv is equal to 3.1156. That means Cp by Cv is greater than 0, greater than 1. That means this value is greater than 1. So my dear, this value it is greater than 1. That means temperature of the tank is higher than temperature of the line. Okay. Now, this is your numerically. That means what is the tank final temperature? What is the tank final temperature is higher than the temperature that the fluid which is flowing in the pipe. Now my dear, you can know you are not doing anything, you are not doing any heat supply, you are not giving any heat, you are not giving any work to the system, but the system temperature is increased as compared to the temperature which are you flowing. That means this is the temperature in the line which is flow, and this is the temperature of the tank. So who is the responsible factor? Who is the responsible factor to increase the temperature of the tank? This is my question. So what is the question here? Why tank temperature will increase. Please tell me, anyone please tell me, why this tank temperature finally increase? Please tell me everyone, why this final temperature of the tank will increase? Why this final temperature of the tank will increase? That means I want to ask, where is the energy to rise the temperature of the air comes from? Where the energy to rise the temperature of air comes from? Please tell me. Please tell me. Please tell me. Who is the responsible fellow to increase the temperature of the tank? Okay. So, to do this, just take one look. What is that? That means, my dear, U of the tank, that means internal energy of the tank is equal to enthalpy of a line. Yes or not? Just now we have to prove it. And what is the enthalpy? U of line plus P into a specific volume of a line. Yes or not? Yes or not? Please tell me. This is what? This is what with the internal energy of the supply line. Energy of supply line. And this is what? This is what with the flow energy this is your flow energy at which fluid entering to the control volume. Fluid entering to the control volume. Entering to the control volume. Okay, okay, okay. Now, this is the internal energy of a line. That means what is the fluid is there? See, either fluid at rest or either fluid is flowing, internal energy is there. There is no any problem. So, the internal energy of the line and internal energy of the tank. So, the tank internal energy will increase by this factor. Yes or not? This is our mathematical term. This factor. That means what is the internal energy of the line is not equal to the internal energy of the tank. Why? Because in the internal energy of the line, this energy will add to the tank. That is the beauty. That means who is the responsible factor to increase the tank temperature? That is your flow work. That means along with the internal energy which is entering to the tank, which is why? Because this internal energy entry to the tank, so it will convert it into internal energy. But that internal energy again will increase when it enter to the control volume. Why? Because along with entry of this internal energy, flow work also will enter. So that flow work will enhance the temperature of the tank. Clear? That means this one converted into the sensible internal energy. Converted into the sensible internal energy, which will increase in temperature of tank. That's it. So the flow work is a responsible factor to increase the temperature. Clear? So what is the cost? So what is the answer here? Why the tank temperature will increase? Why? Because along with the internal energy, you have to add the extra component of energy, that is your flow work. So that flow work is responsible to increase the internal energy. Okay. Now, The second part is that flow work. What is the flow work? So flow work, if you calculate the flow work, is equal to pressure into volume. Yes or not? Pressure into volume. And this is your line. Yes or not? This is your line. Okay. So P of line, specific volume of line. Yes or not? P of line and a specific volume of a line. Now my dear, P of line is there. How to calculate a specific volume of a line? Use ideal gas. So what is that? P into a line into a specific volume of line is equal to R and T of line. Yes or not? So from here you can easily calculate a specific volume of line is equal to R T of line divided by P of line. So if you put P of line is cancelled. So this is what? R T of line. So R you have temperature, line you have, put T temperature, it is in always Kelvin beta. In Kelvin. Put this value, this energy, it is your 816.2 kilojoule per kg. That means what is the important thing here? Ki sir, along with this energy which is converted into the internal energy of the tank, you have to add this much amount of energy to the tank. Why? Because fluid is flowing. So this energy will be responsible. That means you always add this energy due to the flow work. So this energy is not a very minimum, it is a considerable. So due to this energy added, that means this extra component of energy added in the form of flow work, that will enhance the temperature of the system. Clear? Clear? So I hope you understand this concept. So I will end here today and we will discuss in the next session for the next content part. Okay. Up to that, thank you.